All right, everybody, welcome back. We are continuing our notes on Chapter 9 on the atmosphere and severe storms. And we've gone through section 1 and 2, both of them dealing with either energy as it propagates through the atmosphere or what happens as it moves around the atmosphere. We also talked about how water, when it changes phase, let's say you have gaseous water right here or water vapor, when it changes phase and becomes liquid water, it's like a cup right there, right? Liquid water. Energy is either given off or either put in or given off. We call that latent heat. So simply by changing phase, going from gas to liquid or liquid to gas, energy is either given off or put in. So that's been what we've talked about up to this point, kind of the movement of energy around the atmosphere. Now we're going to be talking about the atmosphere itself and what it's made up of. You could think of the atmosphere as being, if the atmosphere were if the Earth were an apple. All right, so I'll draw. I'll draw the Earth right here. Okay, or part of the Earth. The atmosphere could be considered to be kind of like the skin of the apple. I'll make that red so you can actually see it. So just think about how thin the skin of an apple is right there. That's roughly the thickness that the atmosphere is in comparison to the Earth. So it's pretty thin compared to how wide the diameter of the Earth is right there. Well, what's it made up of? Well, it's mostly gas molecules, and we'll talk in the next slide about what gases they are in particular. It also has some solid and liquid particles. We call those aerosols. Aerosols are solid or liquid particles that are suspended in the atmosphere. But also precipitation as well. Precipitation can be solid or liquid, right? It can be snow or rain. But all these are things that can be found in the atmosphere. And of course, the atmosphere, especially the bottom layer that we live in, causes the weather that we experience every single day. We're going to give the bottom layer of the atmosphere a name, which kind of speaks to the fact that the weather is constantly changing. It traps heat. We call that the greenhouse effect. We've talked about how when the Earth re-radiates some radiation, it can't get back out and it's trapped back in, much like a greenhouse does that. So understanding how the atmosphere moves is really critical to understanding severe weather itself. This picture right here is kind of pretty. This is the atmosphere. You can see how this right here is the curvature of the Earth, and it's not very curved because it's a pretty small section of the Earth. But if you were to follow that all the way around, it would of course be a sphere. And so think about how big that sphere would be. The atmosphere isn't very thick at all. One thing the atmosphere does, you've probably seen, is that it breaks light into various different component colors. Red, orange, yellow, there's probably some green in there in the middle, blue, and even some purples as well. When the sun sets, you see the atmosphere behave like a prism and break apart those colors, which is why sunsets look pretty. It separates out the reds from the blues, and you see these different colors. So the atmosphere is thin, but it still does have the ability to scatter different components of radiation and colors. All right, so what is our atmosphere made up of? Well, it's mostly made up of nitrogen, believe it or not. Thankfully, there is oxygen in here, and oxygen travels around in pairs. We call that O2. But most of what the atmosphere is nitrogen. I'll draw that in, green, okay? Nitrogen makes up about 78% of the atmosphere that we breathe, that you're breathing right now. So a good thing for you and for all of us that nitrogen is not poisonous. You just breathe it in, you breathe it right back out. It's not toxic to us, but it certainly doesn't help us breathe. We need oxygen, and oxygen makes up about 21% of the atmosphere's composition, which is about a fifth. All right, so about 1/5 of what you breathe in is oxygen. The other 4/5 is mostly nitrogen. So if you were to add these two up, 78 plus 21, that would give you 99%. All right, so 1%. What is in that last 1% right there? Well, a couple of other different things. You're breathing in a little tiny bit of argon. Argon is in that 1%. You're breathing in water vapor, of course. You're also breathing it out. You can tell that by if you breathe out onto a cold piece of glass or a cold mirror, it fogs up. Well, that's proof that there's water vapor in your breath. but also carbon dioxide as well. Carbon dioxide you breathe in, and carbon dioxide is one of those gases that really traps in heat and keeps our atmosphere warm. It also is blamed for the greenhouse effect. So carbon dioxide can be good, but too much of it can be bad. There's some other elements in there. Believe it or not, you're breathing in helium. All right, you're breathing in neon. Here's erase that. Here's neon right here. You're also breathing in a little tiny bit of hydrogen, and there may be some krypton in there as well, but a little teeny tiny bit, because all these different compounds have to fit in that last 1%. So it's not very much. All right, so let's look at water vapor in particular. For example, water vapor obviously is what clouds are made up of. Well, actually, they come from water vapor. When you look at a cloud, I'll draw it as blue right here. Okay, so here's a cloud you see up in the sky. What you are actually seeing. Oh, by the way, here's the background sky right here. So the cloud itself actually looks white. What you're seeing in that cloud is actually not water vapor, but it's water droplets. Water droplets, they reflect light, and so you see that that cloud is white right there. Water vapor you can't actually see, but clouds actually condense from invisible water vapor. So really, clouds are a function of water vapor. We'll talk about later how as water vapor rises, it cools and condenses and turns into clouds. But they're both different forms of water. So I want to introduce a new term to you, and you probably know this term, but we want to be more accurate about describing it. And that term is humidity. Okay? Humidity is really a measure of how much water vapor or how much moisture there is in the atmosphere. And especially regarding a certain temperature. Because different temperatures of air can hold more or less water vapor. For example, let's say we have an invisible blob of air right here. Okay, it's just an air mass. All right. If it's warmer, it can hold more water vapor in it. Now think about it for a second. If you think, what is something that can hold water? Well, a sponge, right? A sponge can hold water, and so this is very much like air can behave like a sponge. So here's a sponge right here that you might have at your kitchen sink, okay? And it has all those little things in it. All right, it can hold a certain amount of water vapor, but if it's totally full, if it's totally saturated, what's going to happen to that water? It will drop out in the form of little droplets, right? Well, air is the same way. It can hold a certain amount of water vapor. And if it can't hold any more, it falls out in the form of water droplets. Well, the point here is that warm air. That's not a warm color. Warm air, let's make this red. Warm air can hold a lot more water vapor than cold air. Here's cold. I keep getting my colors mixed up. There we go. Cold air right here. Let's make that blue. Cold air cannot hold as much water vapor. Cold air. And so it's like having a smaller sponge, right? So humidity is kind of a generic word. It's just sort of how much water vapor there is. But a certain amount of water vapor, a certain amount of water, will fill warm air, or a big sponge, less than a chunk of cold air or a small sponge. Does that make sense? Like, for example, let me just kind of shade in water. I'll make this light blue, all right? Pretend that you have, I don't know, a certain amount of water vapor. It might fill this air up only about halfway, and it might fill this sponge up only about halfway right there because it has greater capacity. That same amount of water vapor, this amount right here, will fill a colder air mass up more because it can't hold as much. And likewise, a smaller sponge will be filled up more by that same amount of water vapor because it has less capacity. So humidity is kind of a generic word. Really more accurately, we call this relative humidity. Relative humidity. Now, we said, well, what happens if an air mass or a sponge is totally filled up and can't hold it anymore? Well, it drops out, right? It's totally filled up with water vapor. Now, this right here would be filled up with water vapor. So what we can say here is that this right here, this air mass or that sponge, we might say has 100% relative humidity. That means the amount of water vapor that is filling it is all that it can hold. Let's compare that to the other ones, the ones that are warm air or a large sponge, all right? We might say they're only 50%. Should be a 0 right there. 50%, can't write, 50% relative humidity. Does that mean it has less water vapor? No, it's got the same amount of water vapor here and here. But this one, since it has more capacity, the water vapor only fills it up halfway. That's why, relatively speaking, this is only 50% filled. Relatively speaking, this is 100% filled. So, literally, we say that it's the amount of water vapor or ratio of water vapor that the air has compared to how much water vapor saturates or fills the air. That means what it's got versus what it could have. And what it can have all depends on temperature. Remember, we said warm air can hold a lot more water vapor before it's saturated. Cold air can't. It can only hold a little bit before it's saturated. So it's what you've got versus what you could have, and all that depends on temperature. And that makes sense because at nighttime, we have cooler temperatures. And so for a certain amount of water vapor, if the air gets colder, it's like you're squeezing that sponge, you're decreasing the capacity. And what's proof that overnight, or that at nighttime, water falls out of the air and forms droplets? Well, because there's dew on your lawn very oftentimes in the morning after being cold. During the daytime, it gets warmer out, and so the relative humidity decreases. It gets warmer out, and so therefore the air can hold more water vapor, and so the air becomes less relatively humid. It becomes less full because the capacity increases. So you can think of these as the same air mass, just this is warm and this is cold, and the amount of water vapor that it can hold depends on what the temperature is. So that's a little bit about relative humidity. All right, and so as we go up through the atmosphere itself gets colder as we go up, and so that's going to affect what air does regarding its ability to hold water vapor as well. Okay, so as we do move up through the atmosphere, what are some of the layers that we go through? Well, the layer that we're going to focus on the most is called the troposphere. Tropo actually means change. All right, it's either Greek or Latin. It means the change sphere, and that makes sense because all weather exists in the troposphere. All weather. So if you go up through the troposphere and you go up to above the troposphere, there's no more weather. Air is just kind of it's kind of the same all around the world. All right, so the troposphere, where we live, at the very bottom of the atmosphere, contains all the weather. Obviously, since it's at the bottom of the atmosphere, all of Earth's surface is in this layer. And even if you were to go to Mount Everest, you'd only go up to about maybe halfway up through the troposphere. So you wouldn't even get to the top of the troposphere at Mount Everest. It's about, well, from 0, right, because that's the Earth's surface, up to about somewhere between 10 to 12 kilometers in height is the top of the troposphere. And where the top of the troposphere ends, we call it the tropopause. All right, so the troposphere is a layer. The tropopause is, you might say, a boundary, just a line, just an imaginary line. All right, as we go up, we're going to see the temperature decrease. You know that if you were to climb Mount Everest, it would get colder, and that's exactly what happens in the troposphere. All right, so like I said before, all weather exists in the troposphere, including clouds. So all clouds, no matter how high they are all in the troposphere. There's a few names you probably heard of before. Cumulus. Cumulus clouds are those big puffy clouds that you oftentimes see, and usually they indicate fair weather. All right, usually you have a blue sky and a few cumulus clouds. It means it's nice out and you might be outside enjoying the weather. On the other hand, cumulonimbus clouds. Cumulo still means puffy, but nimbus means rain. And these are clouds that are, you might say, puffy, but they build vertically. They rise up like a tower. All right, and so here's the Earth's surface down here at the bottom. All right, well, these clouds rise up. They build and build and build, and they even flatten out. We'll talk about what that feature is a little bit later. We'll call that an anvil head. You may have seen that in some videos and stuff. But cumulonimbus clouds are clouds that build up and they produce rain, because nimbus means rain. So cumulonimbus clouds drop a lot of rain, and they produce a lot of the weather phenomena that we experience, including tornadoes, and they contribute towards hurricanes and all kinds of other things. So these are two primary cloud types that we're going to talk about in the troposphere. So that's it for the troposphere. Actually, I'm going to show you this next diagram real quickly. This is kind of the structure of the atmosphere. You can see here that this is the troposphere, and at this imaginary line is called the tropopause. All right. Mount Everest, it's actually a little bit higher than it should be. Mount Everest only goes up to about halfway through the troposphere. Up above the troposphere, there's no weather, although we do have some interesting things. The next layer up, we call it the stratosphere. We have ozone, which is good because you probably know that ozone, or hopefully you know, that ozone, it blocks ultraviolet rays coming in, or at least blocks a lot of them, which is good news to us because ultraviolet can cause cancer. In the upper atmosphere, we have the mesosphere. Okay, that's this layer right here. In fact, darn it, I didn't want to do that. Well, that was the mesosphere. I just deleted it, and I forget how to bring that back. So we'll just we'll just keep going. And real quickly, here's our last diagram right here. This is what I meant by a cumulonimbus cloud. All right, it builds up. It goes up and up and up and up and up and builds, and it eventually flattens out towards the top of the troposphere right here, and flattens out into an anvil shape that we call an anvil head. Right? But it produces rain. These guys right here, these cumulus clouds, are kind of nice and puffy, and there's lots of blue sky between them. So those are two main cloud types that we're going to talk about. But cumulonimbus clouds are clouds that build up vertically, and we'll talk about why that is a little bit later. So that's a little bit about the lower part of our atmosphere and how we interact with it, and some of the things that are involved in those interactions. So that's it for section 3. I'll ask you to look for section 4 a little bit later. That's going to be talking about the actual weather events themselves. But for the meantime, thank you for watching, and I'll see you on the next video.